Okay, hello everyone. In this lecture and also the following lecture, I'm gonna solve some examples of complex Fourier transforms and how you can solve a PDE using this technique. Um, so before going to the actual way of solving PDEs with this complex Fourier transforms, I want to just give you a simple example of taking a Fourier transform of a function that you can do it later, especially for like complex functions. You can also do and follow similar procedures. And after that, I'm gonna solve an example for how we can use these complex Fourier transforms to find a solution for a given PDE. Okay, so let me get started with a famous function that is particularly used for these Fourier transforms, and especially if you are use these. This is one of the important functions. So in this lecture, we are going to have some examples of Fourier transform. Okay, so the question is calculate the Fourier transform of the following function. Okay, so the function that we have is this: if t over the capital T or period is 1 minus t absolute of t over t when the absolute of t is less than t, and 0 when the absolute of t is greater than t. Okay, so this is a function and I want to take the Fourier transform of this function. Okay, so let's see how it's gonna be. Answer. So this is first I want to show this function. So this is actually a triangular pulse, what we call it. So let me just draw it, and so you take you can have a better understanding that what it is. So if this is t and this is f t, so this function is gonna look like something like this. Here and here, then it's gonna be 0, then it's gonna be 0. So let's see. So here is gonna be 1 at 0, and then after, if t is greater than capital T is gonna be 0, and less than that also is gonna be 0. So this is called a triangular pulse function, and we also show it with tri of t. Okay, so let's see what's going to be the Fourier transform of this function. Okay, so I want to look at that. So what we are going to do is we are gonna take the Fourier transform based on the definition of this function and based on the definition of the Fourier transform, and then solve that. Okay, so I want you to start writing that, and then I will do that myself. So take a little bit of time, start writing the definition of the Fourier transform. Okay, so let me now go ahead. So the Fourier transform of f is gonna be the integral from minus infinity to infinity based on our definition of e to the I beta t ft dt, right? And this equals to the integral from minus infinity to minus t of ei beta t times 0, because from minus infinity to minus t the function is 0, plus the integral from minus t to 0 of e to the I beta t times, it's gonna be 1 plus t over t in this period times dt plus integral of 0 to t of e to the I beta t 1 minus t over t, capital T, of dt plus the integral of t to infinity of e to the I beta t times 0 dt, right? So these terms are going to be 0, right? Because the function is 0 at those places. And so we are left with these two functions, okay? So these two integrals. So I'm going to evaluate one of these integrals because as you see, they are kind of similar to each other, and then use the formula for the other one. Okay, so I'm going to evaluate the integral for this one, minus t of e to the I beta t 1 plus t over t times dt. And what I'm going to do is something that you need to remember from your calculus, but I'm gonna just mention it again, and that is integral by parts. And if you remember, in the previous session we also did that trick. So I'm gonna do the integral by parts technique for solving this. And the way it works is, as I said, so for example, you have this integral of, for example, dfg efx gx, for example. And this is dx, so this is going to be fx gx evaluated at the boundaries, right? And you can also write this as the integral of, take the derivative here, so you can write it as the integral of f prime g plus the integral of g f prime, right? So this was one of the this is the integral by parts. So I'm gonna assume that this is my so my integral, this is gonna be one of the parts here, for example this one, and then so I'm gonna write it as this. I'm gonna write it as the actual functions that were I had evaluated at the boundary, so I'm gonna write it as minus I e to the I beta t 1 plus t over tau over beta. Okay, this is evaluated at minus t and 0. And then for the other one, I'm gonna so I will bring the other one to the left hand side. So this is gonna be minus the integral of the derivative of the other function. Okay, so here, for example, the derivative of the first one, the first function. So if this is your, let me just say, if this can be your f, right? So the first derivative is gonna be I beta over beta, right? So this is gonna give the first one, and this can be your g, right? So the derivative of the second function. Okay, so let me do that. So the derivative of the second function with respect to time is gonna be 1 over t, right? So I'm just gonna write minus I over beta times t. Okay, so this is gonna come out, and then I have the integral of minus t to 0 of a to the I beta t dt. Okay, so this is the general formula for the integral of by parts, but you can take more time if you are not comfortable with it. It's very simple, and then you are gonna get this formula if you use this integral by parts method. Okay, so this is one technique to solve these type of integrals. So let's evaluate this. So if I want to evaluate it as 0 and 1, so at 0, it's going to be minus I times e to the I to the power 0, so it's going to be 1, times 1 plus 0, so it's just 1, over beta, and minus evaluated at minus t. So it's going to be minus I, so minus I, so I just be plus. Then we have e to the power minus I beta t times 1 minus t over t over beta. So this is just going to be 0, right? 1 minus t over t is going to be 0, so the whole thing is going to be 0. And then you have plus I over beta t, the second term here. And then I'm going to take the integral here. So it's going to be I beta t over I beta, right? Evaluated at minus t and 0. So this is going to give me 1 over beta square t times, these i's are going to cancel out, e to the I, so the first term is going to be 1 e to the I beta to power 0 minus e to the minus I beta t, right? Okay, so I am left with minus I over beta plus 1 over beta square t 1 minus e to the power minus I beta t. Okay, so this is the evaluation of the first integral, this integral. I write it as 1. And let's look at the second integral. So the second integral says the integral from 0 to t of 1 minus t over t of e to the power I beta t dt equals to, so similarly I'm just going to write it down and you can calculate it very similarly to this one. So it's going to be I over beta plus 1 over beta squared t 1 minus e to the I beta t. So this is going to be my second integral. So the whole thing is going to be the Fourier transform. Let me write it down like this. So the Fourier transform of ft is going to be 1 plus 2, which is going to be 2 over, so these two terms are going to cancel out, right? This one is going to cancel out with this one, so I'm left with 2 over beta squared t, right? 1 minus e to the power I minus I beta t plus e to the power I beta t over 2, right? Okay, so e to the minus I beta t is nothing other than cosine, based on the definition that we have, beta t minus I sine beta t. And e to the power I beta t is cosine beta t plus I sine beta t. So if you add them up, it's going to be 2 cosine beta t, right? So 1 plus 2 is going to be 2 over beta squared t times 1 minus cosine beta t. And you can write 1 minus cosine beta t using some trigonometric relations as 2 sine square beta t over 2, right? And so this is going to be 4 sine square beta t over 2 over beta square t. And I can write this down as t. So let me write it down here. I can write this down as t times sine beta t over 2 over beta t over 2, just a rearrangement, the whole thing to power 2. You can just check it down. It's very simple. And so this is a definition of a function which we call sinc. So sinc of beta t over 2. So sinc of, let me write it down. So sinc of x is defined as sine of x over x, right? So this is just a definition. So I'm just going to write this down. This is going to be t sinc square of beta t over 2, right? So this is the whole solution for that. And we can say that the Fourier transform of the triangular pulse function is going to be t sine square t over t It's going to be t sinc square. So let me, okay. It's going to be sinc square of beta t over 2. So this is the final Fourier transform of that in the beta space. Okay, so in the beta space, you can plot this and see how does this look like. Okay. So let me just to give you a hint that how does a sinc function look like. So a sinc function looks something like this. So you can plot this one too and see how it's gonna be. So let me just quickly show that a sinc function. So a sinc function looks something like this. So this is x, and this is sinc of x. Okay, so you can see how does this look like when you take the Fourier transform of something like this. Then it's gonna be t sinc square of beta t over 2. Okay, so let me just change something here. So this is better. So if this is beta in the beta space, because we have to do it in the beta space, so this is gonna be beta. And then you can think of it. You can plot this one and see how does the exact shape of this looks like. Okay. So this was just a simple example of how you can take a Fourier transform of a function. Okay, and in the next session, I'm gonna solve an example for solving a PDE using these complex Fourier transform technique.